Yeah.
Then I'm going to welcome everyone for the afternoon parallel session. We're very happy to welcome our first speaker, who is Dongwoo Kim from KIAS, who's going to tell us about 5D BPS quivers and Galois-Klein towers. Please go ahead.
Thanks for introducing me. It's great pleasure for me to give a talk in this nice workshop. So today I'm going to talk about 5D BPS quivers and its index computation. So this work is based on a collaboration with Zihao Duan, who is another postdoc in KIAS, and Pilchen Yi, who is a professor in KIAS. So to make sure that we are on the same page, let me briefly explain what the BPS quiver is and how to construct it in the beginning of the talk, and then proceed the index computation of it. So I will explain what's the obstacle in index computation and how to bypass that difficulty for a class of BPS quivers I introduce. So first, let me explain what BPS quiver is. Actually, this BPS quiver business began in studying 4D gauge theory, in particular D equal to 4 Seibel-Witten type gauge theories. So basically, BPS quiver is effective supersymmetric quantum mechanics, which describes interactions between BPS objects in gauge theory. For instance, when we discuss 4D SU2 theory, we have BPS quiver of 2 noded, which look like this. So it has 2 nodes, and each node represents elementary objects or BPS objects called magnetic monopole and dion. In general, the nodes in BPS quiver represents elementary objects in a theory. So it plays the role of basis, which describes the charge of BPS objects. And then the arrows, which is represented by chiral multiplet of superquantum mechanics. And so this number of arrows is determined by the Schrödinger product between the basis nodes of charges. So the utility of this BPS quiver is that its Witten index, in particular non-zero Witten index, emphasizes or implies that the stable bound states of given charges. So when we are interested in the question like whether this charged object is stable or not in the theory, then we need to assign appropriate charges to each node depending on the basis. And this coefficients Ni will fix the rank of superquantum mechanics which is described by this quiver. Then if we compute the Witten index of this quiver, then we can decide or we can know whether this object is stable or not on the given parameter space of moduli. So to be precise, for example, let me explain you this double boson problem in SU2 Seibel-Witten theory. So because in the charge lattice given by this, double boson is parameterized by 0,2 on a charge lattice, and then magnetic monopole is 1,0 and dion is minus 1,2. This 0,2 can be expanded in terms of this basis, and then we will fix the charge of the rank of these nodes one by one. Then the stability issue of this W boson can be casted into Witten index problem of this effective quantum mechanics. Then wall crossing in the effective quantum mechanics can capture whether this particle is stable or not on a given point of moduli space. So to extend this BPS quiver business from 4D to 5D, let me briefly explain you how we constructed 5D gauge theory first. So this 5D gauge theory is first engineered by so-called geometric engineering in M theory. So we first put M theory on Calabi-Yau 3, then its transverse 5 direction will engineer 5D gauge theory of interest. And in particular, these toric Calabi-Yau 3s are easily parameterized by Z2 lattice diagram, which is called toric diagram. Then in this setup, M branes wrapping on internal 2 or 4 cycles of Calabi-Yau 3-fold singularities give BPS objects in 5D gauge theory. So this picture provides geometric construction of theory and geometric figure or origin to the BPS objects as well. But in 5D gauge theory, one obstacle in constructing BPS quiver is that we have extended BPS objects like monopole strings which world volume is not zero dimension but one dimension. So we need to introduce additional circle to bypass this issue. So this method is suggested by these gentlemen, and their strategy is basically this. So they first consider circle compactified 5D gauge theory and only look at the configuration where these monopole objects or dionic strings are wrapping this circle where this 5D gauge theory is compactified to 4 dimension. Then we can bring our 4D BPS quivers tool to our playground and then mimic our strategy we've used in 4D site. But additional subtlety emerging in this step is because we introduced additional circle, here we need additional nodes which represents KK charges in the theory. In addition to that, we need one more additional node which represents instanton in 5D gauge theory, which becomes elementary objects in 5D. Again, the number of arrows represented by 1D super chiral multiplet is given by the Schrödinger products between the nodes, between the charges of nodes. And one nice strategy suggested by this gentleman is that upon the reduction of D equal 4 KK theory, there is a canonical way to draw 5D BPS quiver because we always have states attributed to D0 brane in this setup. And without D2 or D4 branes, which means electric or magnetic charge. So this basically means we have pure KK modes in our 4D gauge theory, which is constructed by dimensional reduction from 5D. So there we have a states only with these KK charges. And one interesting observation is that we can T-dualize this setup 3 times, and we can end up with this 4D gauge theory, which appears on D3 brane probing toric level threefold we have begun with. And this is famous setup called brane tiling. And there we have many combinatorial tools to engineer 4D n equal 1 gauge theory, which is supported by D3 brane probing toric level threefolds. So thanks to this combinatorial tool, we can easily construct quiver gauge theory now, and this is interpreted as the world volume of D0 brane or KK states in our 4D theory. So now the conclusion or the lesson of this slide is that BPS quiver of pure KK sector is nothing but single D0 brane, and this can be T-dualized to single D3 brane, and then brane tiling setup provides us abelian quiver of brane tiling. So the lesson of, and then if we have multiple D0 branes, then it corresponds to a setup with multiple D3 branes here, then it will raise the rank of gauge nodes to the n. For instance, if we have n D3 or D0 branes. So conclusion is that if we have equal ranked quiver from brane tiling, then it provides us pure KK sector, whereas we have unequal ranked extension to it depicts a BPS quiver for the non-trivial charged sectors. So here we need a map between this charged lattice and gauge node lattice in the quiver, and fortunately, this map, the way to find this map is also sketched by these papers. So for example, in 5D SOA2 gauge theory quiver, 5D SOA2 gauge theory, we have BPS quiver looking like this, which consists of 4 gauge nodes. So here's another remark. So thanks to we could construct BPS quiver from the knowledge of brane tilings, there is another remark we need to make. So one is the quiver always involves fine-tuned spot potential, because this quiver gauge theory first emerges from the 4D n equal 1 theory, which probes Caldera 3 geometry. Also, the Higgs branch of this 4D gauge theory is equal to the toric level threefold we were probing, but that's the story of 4D, and we dimensionally reduce this quiver theory to 1D to cook up 5D BPS quiver, there is additional Coulomb moduli, which pops up in one dimension. So this R3 corresponds to one decoupling sectors. I mean, Coulomb moduli emerging in one decoupled sector of these cyclic quivers. So this is basically how we constructed BPS quivers. And now I will explain how to compute its index. So many of you are familiar with the definition of Witten index. It's nothing but the twisted partition function with fermionic parity weight inserted in between. And the canonical way to compute it is relying on JK residue formula, which usually gave us a Witten index of n equal 4 superquantum mechanics. So it's basically relies on the assumption that this limit, which take circle beta to 0, Witten index is not sensitive to this limit. But we can see the failure of JK residue formula when we apply this formula to our BPS quiver. That's basically because we always have a contamination from continuous spectra in this case. As I mentioned, we began with the engineering of gauge theory with non-compact Calabi-Yau threefold, so there is one non-compact direction, and in addition to that, there is Coulomb moduli R3, which emerged from decoupling sector. So we always suffers from non-compact things in this case. Furthermore, 5D BPS quiver always entail fine-tuned spot potential, as I mentioned. So it has quite conflict with the fact that localization formula written in terms of JQ residue assumed generic superpotential. So case by case, we found some inconsistency in the answer given by localization formula based on JK residue. So to bypass this issue or problem, let me remind what to count. So there are many different strategies we need to apply to different classes of quiver, but today let me focus on abelian quivers only. And this is the very natural thing which emerges from brain tiling setup. So we all know that Witten index basically counts L2 normalizable states. So one thing we need to do is focus on this L2 normalizable Hilbert space only. And the very natural geometric construction of L2 normalizable states comes from this factorization. So for the states when we factorize Hilbert space into two pieces, where one is scattering states along R3, where this is space-time of 4D gauge theory. And the second factor is L2 normalizable states on the Calabi-Yau 3 side. So all the L2 normalizable states in Hilbert space can be constructed geometrically by producing these two. And in terms of moduli space, this first vector, which emerged from decoupled vector multiplet, gave these scattering states, and this a non-trivial cohomologies in Calabi-Yau side will give L2 normalizable states on Calabi-Yau 3. So from this setup, what we need to count to construct the Witten index is L2 cohomology counting over Calabi-Yau 3 side. So there we have 7 elements of L2 cohomology ranging from H0 to H6. And thanks to mathematician, there is a well-known procedure to compute L2 cohomology over Calabi-Yau 3. So first we know that there's pairing between L2 cohomology elements. So this upper part becomes important because we can read lower part as long as we know this upper part. And there is theorem for manifolds with conical metric saying that this Durand cohomology is same to, Durand cohomology of upper piece is same to the Durand cohomology of, L2 cohomology of upper piece. And thanks to pairing between singular homology and Durand cohomology, we can map this Durand to just geometric cycles in the theory, in the Calabi-Yau 3. And thanks to algebraicness and non-compactness of Calabi-Yau 3 side, we can kill several components here, here, here. And the remaining thing is just Hg4, which counts the 4 cycles in Calabi-Yau 3 sides. And because of the pairing I mentioned, this Hg2 and Hg4 is fixed by this geometric 4 cycles. Let me wrap up. So by So basically, within index counts the number of full cycles of tracker level 3 of interest. So index is given by this. And we can refine this result in terms of SU2 symmetry fugacity y this way. And there's a natural interpretation to this fugacity y, which counts the spin of spin of objects in 4D gauge theory. So these two terms is nothing but spin doublets in a gauge theory. And its number of doublet is given by this number of full cycles. For example, for class of Calabi 3, which engineered 5D SUP with Chern-Simon level Q theory, we can apply our strategy to here, ending up with this kind of Witten index for abelian quivers. Here, as you see, H2 and H4 are different, but Witten index is only determined by this H4, not H2. And by hindsight, we can realize that the meaning of this equation. So by generalizing this, we can end up with abelian quiver index is rank times this spin doublet factor. And because this rank labels 5D SCFTs, and we can always apply this result to other types of gauge theory, which comes from deformation of SCFTs in 5D. Also, we can realize that the meaning of these states. So far we have counted neutral KK modes and the one object in the gauge theory without any electric or magnetic charge is nothing but Cartan multiplet in vector multiplets. Sorry, Cartan parts of vector multiplets. So this is why we end up with rank many particles in the theory, because there are rank many Cartan parts, Cartan components in given vector multiplets. So far, I just explained the small sector of BPS spectrum. We can apply another strategy to construct spectrum for non-abelian BPS quivers with higher KK charge and electric or magnetic charges. So because of time limit, I couldn't explain this to you today, but for interested readers, I refer you to these two QR codes, which are linked to another talk I gave in Fudan, Shanghai and Imperial Quiver meetings. So for interested, so this is one tip. So let me summarize this. So I showed that, I just mentioned that the usual JK formula couldn't give a full consistent spectrum of 5D BPS quiver, but this can be bypassed by looking at the geometric origin of states. So for single KK modes, which represents a abelian, which are represented by the abelian quiver, we can apply step-by-step procedure, ending up with this formula for Witten index, and similar or different method can be applied to investigate other Witten index spectrum of theories. So thanks for listening.
Thank you very much. We have time for one or two quick questions. You can use the chat, you can unmute yourself. If you can't, I will give you permission any way you want. I have, maybe if I can ask a short question. So you mentioned at some point you were resourcing to 3 T-dualities, but these were not along the circle that you're compactifying from 5D to 4D, right?
Right, not along that circle.
So what happens if you do T-duality along that circle? Would that be useful for understanding these objects, or?
Basically, to construct BPS quiver, we need to take 4D limit, because we know the BPS quiver story in 4D very well. So we wanted to apply that the conceptual framework to this 5D. So I think integral frame with large circle, it's very hard to apply this BPS quiver story to understand 5D.
So it would be the wrong limit.
Right, but
I see.
But it's basically interesting setup, because in 5D, monopole string is very important objects we have lack of understanding of. So I think in order to understand 5D monopole string more, we need to consider some similar setup, right?
Maybe these KK states would give you would map into the strings, right?
Right, exactly.
Right. If there's no urgent question, it's time to, but it's time to move to the next speaker. Let's thank the speaker again. And Stefano,
yes.
Please share your screen.
Yes. Can you see my screen?
Yes, you can go to full screen mode if you want.
Yes. Everything works?
Yes,
okay.
It's good. So we're very happy to hear next from Stefano Lanza from Utrecht University about the effective field theory, stringy viewpoint on large distances. Please go ahead.
Yes. So first, hello everyone, and I would like to thank the organizers for this nice opportunity to present my work here. So I will try to discuss certain axionic strings that can be coupled to effective field theories. Well, these strings can be particularly useful to explore the modular space of the theory, and they can also be signatures of quantum gravity within effective field theories. So I will organize my talk as follows. First, I will try to very briefly review the main aim of the swampland program, and then I will focus on a conjecture within this program, the distance conjecture. And later I will try to illustrate to you a novel perspective that we proposed on the distance conjecture that is based on axionic strings. Well, whatever I will say is based on this paper that we published 2 months ago with Fernando Marchesano from the IFT Madrid, Luca Martucci from University of Padua, and Irene Valenzuela from Harvard University. So to begin with, let us consider field theories that are built in the following fashion. First, we start from a quantum field theory, and then to these theories, we couple gravity. And let us assume that a theory so built is consistent. For instance, it is anomaly-free. But however, in general, the best that we can do is just to regard these theories as effective field theories that are valid just up to a certain energy cutoff, lambda, because, well, beyond the energy scale lambda, some more complete description should come in. Let us then consider the set of all the possible effective field theories that are built in this way. The question that we want to address is the following. Can these effective field theories be embedded into a full quantum theory of gravity? Or can these effective field theories be truly originated from string theory? Well, in general, we should expect that only a very tiny fraction of these effective field theories admits a quantum gravity completion. And these are said to belong to the landscape of consistent effective field theories, while instead all the rest are said to belong to the swampland, theories which, albeit they look consistent from an effective field theory point of view, however, they do not originate from string theory. And the whole point of the swampland program is trying to determine the boundaries between the landscape and the swampland. And this is typically done by formulating various criteria that these effective field theories need to satisfy in order to be consistent with a quantum gravity completion. And well, these criteria have been named swampland conjectures. During the last years, many of these conjectures have been formulated. For instance, you may be familiar with the global symmetry conjecture, which is, well, far older than all the others. And it states that in any consistent theory of quantum gravity, global symmetries should never be allowed. But however, here I will focus on the distance conjecture, which is instead a constraint on the modular space of the theory. And I will now very briefly review what this conjecture is all about. So let us consider a generic d-dimensional effective field theory, valid up to a certain energy cutoff lambda, that is built out of gravity and a certain set of real scalar fields, this phi I. Well, this phi I span a certain manifold. And since we are assuming that there is no scalar potential in this effective field theory, we may assume that each point P in this manifold actually represents a vacuum of the theory. Moreover, this Gij that appears here can be treated as a metric over this field space. And with this metric, we can introduce the notion of a distance, which can be computed in this manner. What is interesting here, however, is that in these manifolds, there can be singular points for which this metric diverges. And so these singular points can be located at infinite field distances. Well, the swampland distance conjecture tells us that towards these infinite field distance points, something bad is going to happen. In other words, in any consistent theory of quantum gravity, there exists an infinite tower of states that becomes exponentially light at any infinite field distance limits. And this happens for the following reason. If we consider a certain tower of states at a point P, let's say close to the bulk of this manifold, and the same tower at a point Q much closer to the singularity, well, the tower in Q is exponentially lighter than the tower in P. So towards these singularities, the effective field theory is going to break down because we are trying to insert within our effective field theory an infinite tower of states which are very, very light. Ideally, they can eventually be massless. Let me just flesh out a very simple example for which this distance conjecture is realized. Consider, for instance, a 10-dimensional string theory compactified over an S1, so that in 9D we have a modulus, the radian, which parameterizes the size of this S1. Well, if we try to enlarge this S1, sending the radian to infinity, this is an infinite field distance limit, and there exists a tower of states that becomes massless. And this tower of states is just the tower of the Kaluza-Klein modes. Well, as of now, there are many arguments that support these conjectures, but however, these arguments are typically top-down in nature. We can start from a 10-dimensional string theory or eventually M theory and F theory, go down to lower dimension and verify that for each infinite field distance limits, there exists a tower of states that becomes massless. However, here I will try to take an opposite perspective. I will pursue a bottom-up approach. For instance, namely, let us consider the point of view of an EFT theorist that generically does not even know that the effective field theory comes from a string theory. The question that I will try to address is the following. Is there a mechanism within the effective field theory that realizes the distance conjecture? And additionally, can we detect purely from EFT argument that something bad is going to happen towards these infinite field distance limits? Well, our proposal is that the key objects that we need to consider are certain fundamental axionic strings. And I will now specify what I mean. From now on, we'll just focus on 4-dimensional effective field theories. And I will call these strings fundamental because they span, of course, the single direction. They are not thick strings. They cannot be resolved within our effective field theory. Moreover, these strings are electrically coupled to certain gauge 2 forms, and these I are just the electrical charges of the string. Furthermore, these strings are axionic because they are magnetically coupled to axions. These axions are just the electromagnetic dual of these gauge 2 forms. And well, the coupling is such that once we encircle the strings, well, these axions are shifted by the charge of the strings. And moreover, the strings are semi-classical objects. Their tension is greater than the cutoff squared, and this condition will ensure us that the oscillatory modes of these axionic strings can always be neglected within the EFT. And well, whenever these features are realized, we can couple strings to the EFT via this action, which is made up by 2 pieces. The first one is the Namu-Goto term, and it contains the string tension. Eventually, it is field dependent. And here we have the electrical coupling of the string. Now, just I will not take a very small detour to tell you what these strings eventually can be. Now, from a string theory point of view, it is very clear why these strings can be originating in EFTs. For instance, if we consider p branes and rub these p branes over internal p-1 cycles, while these p branes externally look like exactly the strings that I was showing you before. But eventually, these strings can also emerge in Goldstone models as vortices solutions, where the axions are just the Goldstone particles of these models, or eventually they can be astrophysical objects, typically named cosmic strings. Here we'll mostly focus on the first interpretation, and we will need to include these axionic strings in effective field theories that come from string theory. And specifically, we will need axionic strings in n=1 supergravity theories. So let us consider a general supergravity theory built up by certain chiral coordinates. And within these chiral coordinates, which are complex, we will identify the real parts with axions of the theory, while the imaginary parts, well, I will call them succions. And we will assume that the Keller potential just depends on the succions of the theory, so that it is invariant under these axionic shifts. And we will consider a supergravity theory in this form. It is dual to the more standard supergravity action. Here we will have certain scalar fields dual to the succions. They are just the derivative of the Keller potential with respect to the original succions. And here we have the gauge 2 forms, which appear via their field strengths. And to this action, we can couple a supersymmetric string. And what is important here is that this string tension is fully determined by the Keller potential. This tension is just fixed by supersymmetry. Now, what we want to do is to study the back reaction of these supersymmetric strings onto the fields of the theory. And I will just tell you the outcome. As I was anticipating you before, the axions, once we encircle the string, is shifted proportionally to the charge of the string, the electrical charge of the string. And more interestingly, the succions of the theory acquire a logarithmical dependence on this r, which is the radial distance from the string. And well, our idea is to map this back reaction to trajectories within the moduli space, or in other words, we consider within the moduli space trajectories that have exactly the same form as this back reaction. Now, as you can see from this back reaction, once we get closer to the string, when r goes to 0, well, these succions go to infinite, diverge, go to infinity. Well, for a large class of Keller potential, well, these are proper infinite field distance limits. So let's say closer to the string, we can explore distant regions within the moduli space. And well, by the distance conjecture, we should expect that something bad is going to happen towards these limits. And to investigate this, let us look at what happens at the string tension. Well, the string tension apparently goes to 0 as we approach the core of the string. But however, this string tension is also a coupling of our effective field theory. And now we can borrow an interpretation that was put forward by Goldberger, revised, and later used by Polchinski, so that we can regard this back reaction as an RG flow for the string tension. So that this relation is actually rephrased in the following way. As we approach the string tension, this string is becoming weaker and weaker coupled. But if this happens, well, something bad is going to happen for this reason. Well, if the string is becoming weaker and weaker coupled, also the oscillatory modes of the string become lighter and lighter. And actually there is an infinite tower of these oscillatory modes. So to summarize, if we get closer to the string, we are reaching infinite field distance limits, but at the same time we have a tower of states, an infinite tower of states that becomes light. And so we are actually realizing the distance conjecture that I was reviewing you before, and it's purely from an effective field theory point of view. So these observations have actually led us to propose a new conjecture that we call the distant axionic string conjecture, which states the following. All infinite field distance limits of 4-dimensional effective field theories can be realized via these axionic strings. Namely, if we consider an effective field theory defined for a finite cutoff, well, in this effective field theory, we can just explore a finite portion of the moduli space. If we wish to explore also distant regions within the moduli space located at infinite field distances, well, we need such axionic strings. These strings would well, trigger a flow so that eventually the succions can be driven towards these singular limits. Well, let me just flesh out that we, of course, verified this conjecture for a very huge class of string theory models. You can find all of them classified in the paper. And let me also mention that in string EFTs, we can actually have a better understanding of the tower of states that become massless towards these infinite field distance limits. They can be KK or Wending modes, or eventually D0 brane when the theory becomes strongly coupled in the string tension. But however, what is important is that all these towers become massless with a rate that is always fixed by the string tension. This tower becomes massless with an integral power of the string tension. So to conclude, what I try to show you is that these axionic strings can be particularly useful objects in order to explore the modular space of the theories. And specifically, they can drive the fields toward distant regions within the modular space. And well, in the future, it would be certainly interesting to try to test our conjectures also in non-supersymmetric cases, and also try to relate these conjectures with other known conjectures. For instance, the no global symmetry conjecture, or eventually the emergent string conjecture by Lee, Lerche, and Weigand, which is, let's say, quite similar in spirit to this one, but there are some differences. And eventually it would also be interesting to have a slightly more phenomenological understanding of this conjecture, possibly relating this to the Nielsen-Olesen strings or the cosmic strings that appear in literature. So thank you very much for listening.
Thanks a lot. So we have time for some questions.
Yes.
Sungju, please.
Hi, so thank you for the very nice talk. So just a quick question. So,
Sure.
So you can have various different types of such strings in DFT, right? Coupling to different two forms.
Yes,
And
indeed.
can you
Yes.
put, say, two different types of strings together at the same location?
Well, I would say yes. It is just a matter of choice of these electrical charges here.
Yeah, but then what happens? So now you get closer to this sort of superposition of the two strings. Then are they both becoming weakly coupled? There are two different types of strings, and then are you then having two different types of critical strings? Or, just to see what's happening.
Yes, indeed. Also in this case, you would have this, let's say, non-elementary string that becomes weakly coupled.
But you're not supposed to have two different weakly coupled string species in a theory. Isn't that right?
Well, I would say that it depends on the perspective that you wish to consider. On one hand, you can consider separately different kinds of strings. But on the other hand, you can consider also strings which are, let's say, bound states of these elementary strings. It just depends on the, at least from an EFT point of view, on how you choose these electrical charges that appear here. I can give you some examples, like for instance, if you consider D3 branes wrapped on 2 cycles, you can consider, we generate strings in 4D, you can either consider a single D3 brane, which would correspond here to just a charge that is 1, 0, 0, 0, 0, etc. Or eventually you can consider many different D3 branes, and this would lead to charges here which are which do not have just a single entry which is equal to 1, but multiple entries.
Okay, yep, thanks.
Thanks for the question.
Someone, any other questions? Oh, please unmute yourself if you want, Toshi. I think Toshi raised his hand. Toshi for me. I cannot unmute, sorry. Let me try to unmute you. I don't see you.
Hi, thanks. Yeah, so I want to ask a simple question. Is there any connection to weak gravity conjecture for two-form gauge field?
Yes, indeed. Actually, there is a very nice connection with the weak gravity conjecture for these axionic strings. Well, first, let me tell you that we tried to formulate a weak gravity conjecture for these axionic strings in, at least in these, for these theories, in a paper that appeared last year. And what happens is that if you employ the weak gravity conjecture for these fundamental axionic strings, you can actually prove that the distance conjecture is realized toward these infinite field distance limits. In other words, you can demonstrate that a relation like this always appear in the effective field theory. And what is interesting in relation to this weak gravity conjecture is that this lambda here is fully determined by the string extremality factor.
Oh.
So in line of principle, once you know the extremal strings of your theory, you would also know how these the tower of states associated to the string becomes light.
Okay, thanks.
Thanks indeed for the interesting question.
The time is almost over. I had a quick question. Your solutions, you consider back reaction of the metric?
Yes, indeed. We also consider the back reaction of the metric, but yeah, I didn't put it here.
And is there a conical singularity or something like that because of the codimension too?
Yes, indeed. Oh, well, it depends. It depends. It may eventually be a conical singularity, but also some other more complicated singularity.
So that's another reason not to trust the core of the
yes,
string.
indeed.
All right, thank you very much.
Thank you very much indeed. I wish to stop sharing.
We can move to the next speaker. Paul. Yes, perfect. We can see your screen. Right. So Paul Ullman from Uppsala is going to tell us about gauge two-form symmetries in six-dimensional SCFTs coupled to gravity. Please.
Yeah.
Go ahead.
Yeah, I'm audible, right? Okay.
Yeah.
Good. Yeah. Thank you very much, and and also thanks for the opportunity to present this upcoming work, which is coming out together with Andreas Braun, Magdalena Lafors in the next couple of days. And it's really like at the interface of various interesting fields that are popular right now, namely higher form symmetries, six-dimensional SCFTs, and the coupling of gravity of those. Okay, so the main object I want to look at is two-form symmetries. So in order to look at those, I have to have a quick recap of higher form symmetries. So we remember that a conventional zero-form symmetry in d dimensions admits like a one-form current J, and you can get a conserved charge by integrating over that current via some d-1 dimensional space slice. Great, and such a current and such a symmetry naturally acts on some operator V located at points like particles, and so this is the conventional story, and this has been generalized recently, or a couple of years ago, and formalized by Gayatri Zabek, Kabustin Willett to p-form symmetries. So those have a p+1 form current, and essentially the whole logic as above goes through. Now you get a conserved charge when you integrate only over d-1 minus p dimensional space-time slice, and such an object couples to p-dimensional operators. It can be topological, like a one-form symmetry couples electrically to a Wilson line operator, and two-form symmetries then to a Wilson 2 surface operator, and so on and so forth. And it's of course the two-form symmetries that I want to focus on in particular. The key point is, and this has been really facilitated in these papers, that in order to understand your theory fully, you have to, in particular, understand all the topological operators or the symmetries that they act on. So you also have to understand these higher form symmetries to fully understand your theory. Great. So I switch gears now and go to six-dimensional SCFTs. So those SCFTs are, so 6 dimensions is the highest dimensions where superconformal field theories can live. And in the original work by Seiberg and Seiberg-Witten, it has been shown that those SCFTs are special because they are necessarily strongly coupled, and they admit light non-critical strings in their spectrum. So, but moreover, in the last couple of years, it has been explored by extending this higher form symmetry program to those theories that those strings naturally admit a higher form global and self-dual in the electromagnetic sense, discrete two-form symmetry that acts on them. And this precisely happens if the string charge lattice that these strings are charged under, which gives you the 60 SCFT, does not coincide with its dual. So there is a discriminant group that I call GS, which is essentially the difference between the dual string charge lattice and the regular charge lattice. And this is in principle something that should remind you of like a one-form symmetry where the weight lattice doesn't coincide with the root lattice. So it's in principle the same idea. And this discrete two-form symmetry group is also to coincide with so-called defect group. And this defect group can also specify you certain discrete non-abelian two-form fluxes at infinity that has been explored in a couple of papers recently. Okay, but now I want to take such an SCFT and I want to couple them to gravity. And so this is essentially what I want to do. And this might sound like something one should not do, but it's actually something which is very natural. And these light string sectors of some 60 SCFT, they appear very natural in a six-dimensional supergravity theory. And it's in fact very, very important to have them. For example, if I have two supergravity theories with a different number of tensor multiplets, then these theories are oftentimes connected via an SCFT sector or via some light strings. And so therefore, these SCFTs are actually very important to really connect the whole moduli space of six-dimensional supergravity theories with minimal SUSY. Okay, so the way how I get them, this is the quick recap of those, is by take type 2B string theory or F theory and compactify it on some compact space B, which has a certain intersection lattice. And I will call this lambda B. And this lattice is now or like certain curves inside of this space that is specified by this the section lattice lambda B gets wrapped by the three branes, and the three branes then have two legs, so to speak, outside of your compact geometry, and this yields in general massive six-dimensional strings. And the string charges of this D3 branes of the six-dimensional strings, as I say, is precisely specified by this intersection lattice here. So this is the string charge lattice. And if I now choose a certain sublattice inside my compact base that I'm able to shrink, or I'm able to shrink the associated divisors, then those six-dimensional strings become light, and I will reach the SCFT sectors in my supergravity theory. It's essentially the same story as for non-compact theories, but now I have just embedded it into a compact geometry. Okay, great. So now I have done this, and you can ask about certain global symmetries. So in general, there's the quantum gravity law, or maybe one of the original Swampland conjectures, if you wish, that there should be no global symmetries in a quantum gravity, which is broken by black holes or by the black hole evaporation process. So if I have a global symmetry, then I expect that it can either be only broken or gauged. And the question we now want to ask is, so what about these discrete two-form symmetries that are so special to the 60 SCFTs? What about those guys? Are there, when I couple them to a compact background? Okay, so the first ingredient that we want to look at is if these global symmetries can exist. Of course, the intuition is that they cannot, but what is the formal reason for this? And it's actually very simple. A couple of years ago, Seiberg and Waddy Taylor have shown that the string charge lattice lambda B must be unimodular and self-dual. And from that, it directly follows that the discriminant group GS that gives you a global discrete two-form symmetry must be trivial, because lambda B is equal to lambda B star. And you can actually check this really easily. Also, if you take like the background of your favorite n=1 supergravity theory by taking a base B, and it has been shown by Antonella Grassi that such a base can only be a P2 or a Hirzebruch surface Fn, or a blow up thereof at generic points. And you can actually check for those two choices that lambda b is always even self-dual, and it's then a trivial fact that actually a generic blow up, which is the blow up which gives you a -1 curve, so it's a blow up of a generic point, does not contribute at all to a discrete two-form symmetry. So GS, even after blow-ups, will stay the same, and the global symmetry is trivial, and we have just obtained what we expect. Okay, no global two-form symmetries. The more interesting question, of course, is can we gauge such a two-form symmetry then? And what you then want to look at is actually if there can be a group G that has a transformation law where all strings transform trivially under. And since we just showed that that GS is always trivial, like global symmetry is always trivial, you would then expect that G must be gauged. And we will give further evidence for this to be true. So how do we arrange for this? So what you want to do is you want to take like a 60 SCFT, which might be a collection of 60 SCFTs that have a common charge lattice lambda s. And remember, it can be really a product of SCFTs that are not interacting among. And this has a global two-form symmetry, which is just the product of those guys. So now what you want to do is you want to embed this lattice lambda s into the compact lattice lambda b. So now there exists a diagonal subgroup G inside of this GS, under which these strings, like I said, transform trivially exactly if the intersection of the dual lattice of lambda s, of the string charge lattice, intersected with the base lattice modulo the string charge lattice is non-trivial. Yeah, and remember that the dual of lambda s is in general, because we expect to have a two-form symmetry, the dual of this can in general take rational coefficients, so like fractional coefficients. So in principle, like lambda s, these two guys here do not be the same. So this is a little bit of abstract definition, which is very lattice theoretic, simply amounts that the SCFTs and their lattices must not be primitively embedded into the base lattice. So that essentially the group G that we expect to be the gauge two-form symmetry is the torsion part of lambda b modulo the string charge lattice here. Okay, we can make this a bit more precise, or maybe give you an idea what this means in terms of an example. So for this, let's take type 2b on a K3. So this is an n = 2,0 theory, and we choose a non-primitive embedding, like I said, in such a way that we have some shrunken ADE singularities, gamma I here, and you expect to have a gauge two-form symmetry in your compact K3. So there's an SCFT sector which is parametrized, so to speak, by these ADE singularities, gamma I modulo G, and the G is the gauging. Okay, so now what you can do is you can compactify this theory on a circle and go to 5D. Then, it is well known, you can, the strings that wrap this additional circles, they become the W boson of a 5-dimensional gauge group, which is now of type gamma I mod G. And the key idea here is that if I put a two-form symmetry on a circle, it becomes a one-form symmetry in a lower dimensional theory. Well, at least part of it becomes a one-form symmetry. So now what you expect is in 5 dimensions that you get a gauge group, which is non-simply connected, because the two-form modding that you have in 6D is now a one-form modding you have in 5D. Yeah? And of course, you can double check this because this setup here by if you want trivial MF theory duality, is dual to M theory on T2 times K3. So how can you double check that this 5D theory here is really non-simply connected? Now, of course, you have a certain divisor relation that I will talk about in a second, but you can get more concrete if you add one additional assumption, which is not necessarily to be the case, but for the sake of argument, now it works. So now we assume that the K3 is also elliptic. In such a case, you can show that this group G of gauge 2 form symmetries is in fact precisely the model Weil group of K3. So now the SCFT sector lambda S are precisely those fibril curves that do not hit the section and that you mod out. And this is precisely the finite part of the model Weil group. And since now this K3 here is elliptic, there is a second lift I can do. So now I can lift this whole theory in 5D if you want, because you have here another elliptic fibration sitting in. You can lift this whole setup to an 8-dimensional F-theory geometry on K3 with a finite model Weil group. And for those guys, it is known that that you have a non-simply connected gauge group, and that this one is actually anomally consistent. So from this argument, it's clear that since this lift here is just a T3 compactification that lifts to 5D, you will definitely get a 5-dimensional gauge theory with a non-simply, or supergravity theory with a non-simply connected gauge group. But we also know that this is the same theory that comes from type 2B from a supergravity theory with 2,0 supersymmetry and these SCFT sectors, and they go to the same theory. So so this gives of course evidence that this gauge 2 form symmetry that you have here must be correct. So now I want to present another example, which is which comes with minimal supersymmetry, which should illustrate you how it works in other setups and how you can exactly read off how this embedding is. And for this, I take F theory compactified on a base, which is just a Z5 quotient of P2. You have a toric diagram that is given like this via these vertices here. And as you can already see, the vertices are precisely such that they span a lattice of finite index, of index 5 in Z2. Okay, so now we have a couple of singular patches here. It's strictly 3 of them, and you can resolve them via these green resolution divisors. You get them from adding the rays that split the cones. And so these are the guys. And if you look at those, this is a bunch of -3, -2 curves that you have here. And you have an Z5 2,0 theory sitting here. So you have a bunch of collections of SCFTs, a couple of like one 2,0 and one 1,0 type, and they all have a global 2-form symmetry of Z5. Okay. Of course, we expect that to be broken, but now we can argue and we can exactly get how the exact embedding of this gauging is that happens here. Okay, and how this works is precisely by using the tensor branch geometry that we have here. Okay, so what we can now do is we can use a little bit of toric geometry by writing down a certain divisor relation, which is given like this, where we can use that these edge vertices here are a lattice of finite index, and oh, I have to speed up, and that this is a lattice of finite index, and you get this relation here. And note that these are all integral divisors, so intersections with these guys will always be integral numbers. And this means that any curve that sits in your base must have a 0 mod 5 intersection with this guys. And since these green dudes here are the resolution divisors of your SCFT, that means in order to fulfill this condition here, there must be constrained charges under these tensors that upon shrinking give you the SCFT sector. And this tells you that your BPS string charges must be restricted by this gamma 5 object here, or by the sigma 5 object here. Okay, so let me summarize then. Yeah, this is just everything we did. This proposal we give here is that you have this non-primitive embedding is actually very, very general, and it works for actually more than just 2-form symmetries. And I showed you it restricts the BPS strings, and it actually also works for little string theories. And you can check this proposal actually via various dualities also to the heterotic string. And it would now be nice to, in the future, for example, after we publish this paper, to also double check if this gauging is visible in enumerative invariants like Cooper-Kummer buffer invariants. Consider gauge two-form anomaly cancellation, just as has been partially been done for one-form symmetries that are gauged, and to classify toric bases and their symmetries. But yeah, I'm finished so far. Thank you very much.
Thank you very much. Right, we have time for one brief question. If you want to ask a question, raise your hand and I will unmute you if you are muted. I'm not sure if I'm missing a point here. Otherwise, so you can compactify any 6D SCFT that you can imagine, like, or
No.
there is no obstructions. So.
No, there's for sure going to be an obstruction, because first of all, that's very direct. Is that the landscape of 6D SCFTs is infinite. So there's like, for example, even for 2,0 theories, the SU2, SUN type of singularities, you can take n to infinity, which in some cases is even what you want. But a K3 has only has a fixed Euler number. You cannot put just any of those guys in. So already from that, it's clear that it's that this is going to be restricted. But the question that we had here is, of course, and then usually these guys, or even the 1,0 theories, they have like flavor symmetries, various flavor symmetries, and when you put those in a compact geometry, generically those are broken. In some cases, they can be gauged. You can see that for the flavor symmetry very directly, and even this gauging of this flavor symmetries gives you in general restrictions, because you cannot gauge just whatever you want. Also, 1,0 theories are very constrained, and we essentially try to extend this to this possibility of these discrete two-form symmetries, because this is really something, if you want, very non-perturbative and very, very specific to these 6D SCFTs.
No. Yeah. So okay, I expected something. Thank you. Yes. Let's move on then to the final speaker of the session, Thorsten. Welcome. And we're ready to introduce Thorsten Szymanek from Vienna University, who's going to tell us about C5, symmetries in F-theory, homological projective duality, and modular forms. Please go ahead.
Yes, thank you for the introduction and for inviting me to present some upcoming work in this parallel session. So let me start by giving you some context and motivation for what I'm going to talk about. So it has been the result of a series of work in recent years, going back to the 90s actually, that if you consider the topological string on torus fibered Calabi-Yau threefolds, for example, then the topological string partition function exhibits modular properties. And in particular, if you have a fibration which only admits n sections, at least for n less equal to 4, then the partition function can be expanded in terms of gamma 1 n weak Jacobi forms. So let me first start by telling you what an n section is. If you have a fibration, it does not necessarily have a section. If you have a torus fibration with a section, it is called elliptic, but in general, you only have n sections. And I show you here the example of a 2-section, which intersects the generic fiber twice, but the intersection points experience monodromy along the base. So this is not just the union of 2 sections. And this determines the modular properties of the topological string. And one can argue that this is in essence a result of certain monodromies in the stringy Kähler moduli space. And now, why is it interesting to consider torus fibered Calabi-Yau threefolds? One reason is certainly that they are abundant. So there's evidence that if you pick a random Calabi-Yau, then it will almost always exhibit a torus fibration structure. And perhaps even more importantly, they play a central role in the network of string dualities, partly due to their relevance as F-theory compactification spaces. So in this talk, I want to extend this to n equal 5, so genus 1 fibrations with 5 sections. And the point I want to make is that this is not just an increase by 1 and we play the same game, but that the n equal 5 case sheds light on various new phenomena, and in that way connects all of these different topics that I show on the slide. And this is based on very soon to be published work together with Johanna Knapp and Emanuel Scheidegg. Now, let me give you some idea of how the modular properties manifest in the topological string partition function. If you have a genus 1 fibration with n sections, it is conjectured that the topological string partition function can be expanded in the following way. And the expansion parameter are the exponentiated complexified volumes of curves in the base of the fibration, which are slightly shifted for technical reasons. And then the coefficients depend on a modular parameter, which is 1 over n times the complexified volume of the torus fiber. And you have elliptic parameters, which amount to the volumes of certain components of reducible fibers, or in 5 dimensions, you can interpret them as Coulomb branch parameters of the theory. And then the conjecture is that these coefficients in the expansion are actually gamma 1n lattice Jacobi forms. And the only point I want you to take away here is that this allows you to obtain all genus results for the topological string on compact Calabi-Yau threefolds. Now, I told you that this can be seen as a consequence of modularity of monodromies in the stringy Kähler moduli space. And the idea is that you interpret these complexified volumes, tau, m, and t, as the charges of two branes, and then certain generic autoequivalences act on the category of branes. And at least for n less equal to 4, we have shown that this generates a gamma 1n action. And so you need basically two monodromies for that. The first is, the first is the well-known B-field shift, which just shifts, for example, tau by 1 or m by 1. But more importantly, you have in these torus fibrations what you can see as a fiber-wise conifold monodromy, which acts in the following way. And then one can argue that these two monodromies, together with the automorphic properties of the topological string and the so-called holomorphic anomaly equations, basically imply this expansion in terms of weak Jacobi forms. So let me briefly give you an idea of where these monodromies sit in the stringy Kähler moduli space. So here's the example of the moduli space of a genus 1 fibration with 2 sections over P2, more precisely the GLSM moduli space. And so on the upper right corner, you have the large volume phase where the GLSM flows to a nonlinear sigma model on the Calabi-Yau, and the monodromies around this large volume limit correspond to the B-field shifts. But then you also have a wall which separates this geometric phase from the formally negative volume of the fiber phase, which would here be a hybrid phase over P2. And if you follow a path around this wall, going back to the large volume limit, then you get this U monodromy. And as I said, together, these basically imply the modular properties. Now, the reason I'm telling you this is that it leads to the first puzzle in the context of 5 sections, because for n greater to 4, the group gamma 1n has more than 2 generators. In particular, for 5 sections, it has 3 generators. So the first question that we are faced with is where this third generator sits in the moduli space of the corresponding genus 1 fibrations. Now, to answer this question, it would be nice to look at examples of genus 1 fibrations with 5 sections. And what we can use here is the fact that you have certain normal forms for genus 1 fibrations with various sections. If you have an elliptic fibration with a section, you can map it into a fibration of Weierstrass curves that take this well-known generic form as a hypersurface in P1 to 3. For example, if you have 4 sections, you can map it into an intersection of 2 quadrics in P3. And in all cases, for 1 to 4, you get complete intersections in toric varieties. And you can take these normal forms and engineer toric complete intersection Calabi-Yau's, which have the desired n sections. But what about the normal form for n equal to 5? And here things get a little bit more complicated, because genus 1 curve with the 5-point can be mapped into a Pfaffian curve in P4. And to get this curve, what you do is you consider an anti-symmetric 5x5 matrix A with entries linear and the homogeneous coordinates on P4. And then the genus 1 curve is the locus where the rank of this matrix drops below 3. And equivalently, you can see this as the vanishing locus of the 4x4 Pfaffians of this matrix. And this curve is in particular not a complete intersection. But you actually have a complete intersection description, which is dual, but it is not inside a toric variety, but inside a Grassmannian. And to obtain this, you can use the Plücker embedding to embed the Grassmannian of 2 planes in 5 space into P9, which is also defined by 4x4 Pfaffians. And if you then intersect this with the generic P4 subspace in P9, you get the same genus 1 curve. And in that way, you can also represent it as a codimension 5 complete intersection in this Grassmannian. And this is, in a sense, one of the simplest examples of what is called homological projective duality, which has been developed by Kuznetsov in 2005. And you can also see this as the one-fold analogon of the so-called Rotland Calabi-Yau, which was one of the first examples of a non-torically realized Calabi-Yau that has been studied in detail. Now, to come back to the question of the generators of this gamma 1,5 group, what we can first do is just study the curve, which will be our generic fiber. So a gauge linear sigma model for this curve has been constructed by Hori and Johanna Knapp in 2014. It's a non-abelian GLSM with the U2 gauge group, and then you can obtain the quantum periods using a localization calculation. And now if we, for example, look at this modular space, first of all, we see we have 2 geometric phases, one corresponding to the Grassmannian curve and one corresponding to the Pfaffian curve. And now the special phenomenon is that this is not separated by 1 conifold point, but by 2 conifold points, which is kind of a characteristic properties of these non-abelian GLSMs. Now, using these localization calculation and the periods, we can perform a numeric analytic continuation to see how the monodromies act on the complexified volume of the curve. And we see that, for example, starting on the Grassmannian curve, the monodromy around this first conifold locus gives us just the U transformation, which is expected. But then we can also take the monodromy around the second conifold point, and this indeed gives us the second, and together with the B field shift, the third generator of the gamma 1,5 group. And of course, we can play the same game based on the Pfaffian curve, and we get the same monodromies. So in this way, we see how, at least at the level of the fiber, we get this additional monodromy. And one can generally argue that these monodromies embed into the modular space of the fibration. And for that reason, we expect that we can apply the modular bootstrap to the corresponding Calabi-Yaus. But now, how do we actually get Calabi-Yau threefolds out of these curves? And the idea is that you promote the coefficients inside this matrix A to coefficients to sections of bundles on base of the fibration. And then we want to construct the associated non-abelian gauge linear sigma model, and again use localization calculation to obtain the quantum periods. But the question that arises now is which choices of bundles lead to smooth vibrations, which in this non-toric case is highly non-trivial to answer from a purely geometric perspective. And it also leads to a second puzzle, what these 2 geometric phases, the Pfaffian and the Grassmannian phase, mean in the context of the fibration. Now, to solve the first problem, to get bundles leading to smooth vibrations, we actually resort to F-theory. And to this end, let me give you a very brief introduction how F-theory relates the geometry to the 6-dimensional physics. The first important thing is that you have multiple end sections. For us, the case of multiple sections in an elliptic vibration will be important. You get an abelian part of the gauge group. But if you do not have a section and only end sections, you get a discrete part of the gauge group, a Zn factor. This can also be realized by having, for example, an elliptic vibration which has torsional 3 forms and will in general be singular. But we want to use this now first to obtain genus 1 vibrations. And to this end, you can note that if you have an abelian group U1 and you have charge n matter, you can perform a Higgs transition to break this U1 to a Zn. And now this geometrically corresponds to an extremal transition from an elliptic transition to, in our case, a genus 1 fibration. So the strategy that we use is actually to start by engineering elliptic fibrations by constructing generic elliptic fibers as complete intersections in toric varieties. Then we use a technique based on Gopal-Kumar-Waffa invariance, which Paul and I developed in 2019 to obtain base-independent expressions for the corresponding F-theory spectra. So in that way, we can check that the corresponding F-theory vacua indeed allows such a Higgs transition. And we can then construct all smooth vibrations with these elliptic fibers, for example, over P2, which lead to a sufficient number of Higgs multiplets. And in this way, we obtain the Pika-Fuchs operators that annihilate the quantum periods for genus 1 vibrations with 5 sections over P2. And we can then deduce all of the topological invariants from the Gopal-Kumar-Waffa invariance and certain generic properties that they exhibit for genus 1 vibrations. And as a bonus of this construction, we also obtain the first F-theory vacua with charge 5 matter. So the circle of ideas here is that we use these extremal transitions, and then we use the F-theory spectra that we get from the Gopal-Kumar-Waffa invariance and the base-independent expressions for the multiplicities to guess the corresponding bundles. Then via an algebrogeometric study and using several spectral sequences, we can calculate the corresponding topological invariance to cross-check. We can also engineer a corresponding non-abelian engaged linear sigma model and obtain the quantum periods via localization, and again cross-check with the results that we gain from the extremal transition. And in this way, we obtain 23 examples of vibrations over P2. Now, having these examples at hand, we want to come back to the puzzle of the two geometric phases and what they mean in the context of F-theory and in the context of genus 1 vibrations. So this is now a picture of the moduli space of the genus 1 vibration with 5 sections, or the GLSM moduli space. And what you have here are, first of all, in the small base limit or negative base volume limit, certain phases which depend on the particular vibration. But then in the large base limit, you have generic phases, namely one phase corresponding to a vibration of complete intersection curves in Grassmannian, and this other phase which corresponds to a vibration of Pfaffian curves. And again, they are separated by these two conifold loci with the monodromies leading to the modular properties of the topological string. So to explain you the geometric significance of these two phases, let me give you a very brief technical interlude. If you have a genus 1 vibration, then you can always construct an associated elliptic vibration by essentially taking the relative moduli space of degree line bundles on that curve, which is called the Jacobian vibration. And F-theory only cares about the Jacobian vibration associated to genus 1 vibration. So you can consider F-theory on X or on J of X, and you get the same physics. But for M-theory, the physics on X and J and X is actually different. And it is a highly non-trivial fact that the genus 1 vibrations, which share the same Jacobian vibrations, form a group structure, the so-called Tate-Schaffer-Ravitch group. And the elements of this group are not just a geometry, but they are geometries equipped with an action of the Jacobian vibration. And for example, in general, if you have a geometry X with an action A, then the inverse element in this group is the geometry X with the inverse action. And these are in general different elements of this Tate-Schaffer-Ravitch group. So this might already give you a hint of how to interpret these two phases. And in fact, we make an argument in this paper using various pieces of evidence, so to say, that the genus 1 vibrations associated to these two phases indeed correspond to different elements of the Tate-Schaffer-Ravitch group, different genus 1 vibrations sharing the same Jacobian vibration and thus leading to the same F-theory physics. And what is perhaps even more striking is that we then perform the modular bootstrap of the topological string partition function, express it in terms of gamma 1,5 Jacobi forms. And it turns out that the results for the two different phases are actually related by a transformation with an element of gamma 0.5. And one way to see this is that if we go back to the modular space of the fiber, we can now start, for example, at the Grassmannian curve. And now we do not perform an analytic continuation along a loop, but we analytically continue from the Grassmannian curve to the Pfaffian curve. And the corresponding action on tau is indeed an involution, which is an element of the gamma naught 5 group, and the topological string partition functions transform as vector valued Jacobi forms under this action. And there's even more to the story. So as a more general conjecture, where I only give you a cartoon version at this point, the topological string partition function on all elements of the Tate-Schoffer-Ravitch group and for all n in n sections are actually related by these kinds of modular transformations. So the aspects of the story for 5 sections that I have told you a bit about now is what we will cover in this soon to be published paper with Johanna Knapp and Emanuel Scheidegger. And then this more general conjecture for different ends I will elaborate on in a spin-off paper, which will also soon to be published. So let me briefly summarize. We perform a detailed study of these torus-fibered Calabi-Yau manifolds with 5 sections and obtain several examples using extremal transitions and non-abelian engaged linear sigma models. We observe that we always get a Pfaffian and a Grassmannian phase, and those are derived equivalent via fiber-wise homological projective duality. And we argue that they indeed share the same Jacobian vibration, and in this way lead to all of the 4 non-elliptic geometries in the Z5 Tate-Schoffer-Ravitch group. We show that the modular bootstrap extends to the 5-section case and that the topologic string partition function is expressible in gamma 1,5 Jacobi forms. But as a new phenomenon, these now transform vector valued under this fiber-wise homological projective duality, which acts via an element of gamma naught 5. And we also show that this can be seen as a consequence of Higgs transitions in M and F theory. So with this, I have exhausted my time, and let me thank you for your attention.
Thank you very much. So if anybody has a question, we can take it now. Raise your hand if you wish. Sangyu, please go ahead. You can unmute yourself, I think. Yeah.
Hi, thank you for the very nice talk. So just a naive question. So from this perspective, could you say whether you can, in principle, build a model for larger n, even larger n?
Yes, that's a very good question. So I mean, these normal forms for n1 to 4 are well known, and for n equal 5 have been studied by Tom Fisher extensively. Now, I'm not aware of a result in the literature on the normal forms for 6 sections, but we think we know how those can be constructed, and this will also be the story of some follow-up that we are working on currently. But as soon as it comes to n equals 7, we have no idea what a normal form would look like. And there's even some reason to argue that genus 1 vibrations with 7 sections should not even exist, at least not 3-folds or higher.
Okay, thank you.
Thank you for your
Paul,
question.
I think you can unmute yourself. Yes.
Yeah. No, I have actually like a follow-up question to this, which you might look at this this action of gamma naught n for larger n, and you know that so one thing that we did in this other paper for torsion sections is that you can try to map this to this modular curve in which the monotomies have to be contained, and if you crank up the n at some point, even for torsion points, the modular curve becomes not the P1 anymore, and I would expect something similar to hold for gamma naught n too. I just don't know.
Yes, exactly. So this is kind of a mirror dual picture. So I would argue that this generic genus 1 curve with an endpoint is mirror dual to the generic elliptic curve with n torsion. It is very difficult to make this argument without falling into circular reasoning, but at least for n less equal to 5, this is the case. And then, as you said, for some n, the modular curve, which you then factor through in the modular space, becomes non-simply connected, which is excluded by at least swampland conjectures. So it is conjectured that the modular space of theory of quantum gravity should be simply connected. But this argument, I think the genus increases at n equals 17. And I would expect that there's a much lower bound. But from this quantum gravity argument, you would expect that at least beyond n equals 17, you cannot have such a vibration. Yes.
Great, cool, thanks.
Yeah, thank you for your question. It would be very interesting to make this mirror duality between n sections and n torsion precise.
Sure.
And at this point, it's always a bit of hindsight, because when we show we have this gamma 1n monodromy, then you kind of see that it is dual to the complex structure modular space of the curve with n torsion. But it is difficult to make that argument without already knowing the monodromy before.
Right. Great. Thanks.
Yeah, thank you.
Right, thank you very much. I think I don't see any more raised hands. I think we can wrap up this session by thanking Thorsten and the rest of the speakers. Again, thanks for the nice talks. And we will meet in 25 minutes, 5:20 Korean time, we will just take a little step and learn all about the status and progress in neutrino oscillations. So I hope to see you all there. See you later.
Bye. Bye to you all.
Bye, Stefano.
Hope to see you in person soon.
Yeah.
And
Yeah. Let's hope soon.